Now we're going to look at one of the most important problems in quantum mechanics, and the one that was a remarkable success for Schrödinger's wave equation, the hydrogen atom. Understanding the hydrogen atom sets us up to understand the nature of atoms and the basics of chemical elements, so it's of profound basic and practical importance. It also gives us much of the nomenclature which we'll use to describe atoms. The hydrogen atom is also mathematically exactly solvable, so it's an excellent exercise in quantum mechanics. It's somewhat more difficult to solve than the very simple particle in a box and the harmonic oscillator problems we've looked at so far, but nonetheless we can lay out the solution in its entirety without major difficulties. Our discussion of angular momentum and the spherical harmonic eigenfunctions has already dealt with a major part of the problem for us. In addition to its impact in chemistry, we can also use the hydrogen atom solutions in engineering. In semiconductors, for example, the phenomenon of what are called Wannier excitons uses a scaled version of the hydrogen atom solution, and that is essential in explaining the actual optical absorption of semiconductors in optoelectronic devices. There's another reason why the hydrogen atom is also an excellent tutorial problem. With the hydrogen atom, we have to deal with a system with not one, but two particles, the electron and the proton. The wave function of two particles is somewhat more sophisticated and interesting than we might have thought, and we'll start by thinking about just how we're going to extend our quantum mechanics to handle more than one particle.
So how then should we tackle this problem of two particles, the electron and the proton? Well, what we do first of all is we start by generalizing the Schrödinger equation. And now we mean quite generally, for example, for time-independent problems, that the Hamiltonian operating on the wave function is equal to the energy times the wave function. Now, this wave function, we presume, could now be the wave function of two particles or possibly more. And this Hamiltonian would be the energy operator for these two particles or possibly more particles. So this is a generalization of Schrödinger's equation. The Hamiltonian is the Hamiltonian of our whole system now of however many particles we have in it. And the energy will be the energy of the whole system, and the wave function will be the wave function of the whole system. So, as I said, explicitly now, the Hamiltonian is the operator representing the energy of the entire system, and psi is the wave function representing the state of the entire system, no matter how many particles it has in it. Now, for the hydrogen atom, there are two particles, the electron and the proton, and each of these has a set of coordinates associated with it. So we have x, y, and z coordinates for the electron, which we've indicated with this subscript e, and x, y, and z coordinates for the proton, which we've indicated with the subscript p. The wave function will therefore, in general, be a function of all six of these coordinates.
This may not have been what you were expecting. Perhaps you were thinking that we could just have a wave function for the electron, a function of the electron's x and y and z coordinates, and a wave function for the proton, a function of its x and y and z coordinates. But in fact, we have one function for all six coordinates. Why is this? Well, an analogy may help here. Think of a collection of dancing couples, performing a dance like a waltz, for example. In a waltz, the man and the woman in the couple move round the dance floor and they turn round one another as they go round, and approximately they will eventually circle all the way around the dance floor. Now, we could write down a probability distribution for the male dancers on the dance floor. Since the dancers do get round the entire room during the course of the dance, their probability distribution would be spread over the whole dance floor. Similarly, for the female dancers, their probability distribution would be spread around the room. But those individual probability distributions would miss the fact that the man and the woman are generally to be found together as they dance in a couple. Though the probability of finding a male dancer is a distribution that spreads over most of the dance floor, and similarly for the female dancer, the probability of finding a male dancer beside a female dancer is very high since they're dancing in pairs. Similarly, writing down the probability function for the male and the female would completely miss this fact. Our description of the electron and the proton needs to explain similar phenomena. With a hydrogen atom in a box, the hydrogen atom might well be found anywhere in the box. The electron could similarly be found anywhere inside the box, as could the proton. But wherever we find the proton, we are very likely to find the electron close by. Having the wave function be a function of all 6 coordinates allows us to handle situations like this. But 2 separate wave functions, one for the electron and one for the proton, each of 3 coordinates, in general would not. Now, in some specific situations, we'll find that we can simplify back to something equivalent to different wave functions, each with 3 coordinates. For a hydrogen atom in free space, we can do this, but these individual 3-coordinate wave functions are not the wave functions of the electron and of the proton separately. This does mean that in quantum mechanics with large numbers of particles, the full description would require wave functions with very large numbers of coordinates. 3 particles would require 9 coordinates. A small lump of material would require a wave function with something like 10 to the power 23 coordinates. Now, in practice, we can sometimes find ways to simplify such problems by making key assumptions. And this is indeed what we have to do to describe the physics of materials. But underneath all those simplifications is the fact that we really have one multiple particle wave function with possibly a very large number of arguments. So if we have n particles, then we need a mathematical space with 3 times n dimensions, instead of just the 3 dimensions of normal Cartesian space for one particle. Such a mathematical space is sometimes called a configuration space. This should not be confused with the Hilbert space. The configuration space may have 3 dimensions for each particle. The Hilbert space has possibly an infinite number of dimensions for each degree of freedom, that is, for each coordinate direction for each particle.